Hello, my name is Carter Dugan. I am the president of the Wireless Communications Enterprise, an ECE enterprise here at Michigan Technological University. I am also the team lead for the Systems Engineering Research Center team for WCE, where we have been working on the high data rate video transfer drone module project. Thank you for giving my team your time and reviewing our video presentation for our project, which is now in its second semester at WCE and its third semester total at Michigan Tech. It is my pleasure to present to you today and represent the CERC team, Michigan Tech, and the Enterprise program on the behalf of WCE. I would like to start by introducing the rest of my team, consisting of hardware engineer Ricky Ritelny, a third-year electrical engineering major, systems engineer Devin Farmer, a senior computer engineering major, hardware engineer Zachary Sugars, a junior computer engineering major, and myself, a systems engineer and senior computer engineering major. I would also like to introduce Electrical and Computer Engineering teaching professor and WCE faculty advisor Mr. Christopher Cischke, who has provided mentorship and guidance to not only my team, but every team at WCE, as well as U.S. Army Staff Sergeant Michael Tippett, who was appointed by CERC to be the mentor for my team throughout our time with this project over the last 2 semesters. My team was tasked with developing a module capable of being attached to a quadcopter drone and transferring video footage over cellular networks. The general concept is to allow the user to communicate with the drone using a cell tower as a middleman, theoretically allowing for infinite range video transmission as long as a cell tower connection is maintained between the drone and the user. One of the more interesting aspects of our project was the open-ended nature of the task. In terms of constraints, the only real constraint we were given was that our module must be 200 grams or less to meet the maximum load requirements. Obviously, emphasis on the security was given, but overall the team was given a lot of freedom in their approach to and execution of the design process for this project. We set simple objectives for ourselves. One of our goals was to develop a portable solution, meaning our implementation of the module would be easy to adapt and change by future teams. We also wanted to deliver a quality product when it came to performance, reducing latency and improving video quality to ensure responsiveness and ease of use. Finally, and perhaps most importantly, we wanted our product to be secure by implementing reliable transfer and encryption of the data that was being transmitted and received. Our approach was broken up into 5 parts, each with several sub-processes before transitioning to the next major milestone in the project. We first established a plan for our approach through software, as software choice and configuration would make up a large portion of this project. With portability in mind, our first move was to select a platform that allowed us to implement widely used software for streaming and security. Moving on from the software outline, we then began to work on prototyping the hardware. The main computing device would be selected based on the platform chosen at the beginning of the first stage. Afterwards, we would move on to select hardware for wireless communication and then for video capture and encoding itself. After the prototyping stage, the team would begin work on the final custom hardware implementation on actual PCB. This is where the portability aspect of our design choices would begin to pay off. Due to the time-sensitive nature of enterprise projects, having our transition from prototyping to custom hardware be as seamless as possible would provide us with the most time to make progress. This is where we would need to take consideration of the compatibility between our choice of hardware and our choice of software. Adjustments would inevitably need to be made in this regard, but the objective was to minimize them. We would then implement this design on a custom PCB. By this point, testing would have already been done on the prototype hardware, but now it would be time to do the same for the PCB design. We would begin by testing the wireless data transfer over a wireless local area network, which are usually Wi-Fi networks. We would then repeat that process, but over a cellular network instead. Adjustments would need to be made in response to discrepancies identified during the testing process, but after those are made, we could move on to refining the final product. The initial hardware design stage involved building the drone and configuring the first prototype of the cellular video transfer module. For the drone, we opted to use a Pixhawk 2.4.8 flight controller for quick construction. That way we could get the drone flying quickly and start working on the module itself. We used 10-inch carbon fiber propellers and a lithium polymer 12-volt battery. To supply power to the main system from the same battery, we used a buck converter to step the voltage down to 5 volts. The main computer for the module was a Raspberry Pi Model 4B, fitted with a 4-core 64-bit ARM processor and 4 GB of DDR4 RAM. To achieve wireless communication over cellular networks, we used a 6-fab LTE base hat that fit directly onto the Pi. The base hat had space for a radio card and a SIM card, and for that we chose a M.2 3G radio chip and a prepaid Boost Mobile SIM card. From there, we prototyped and tested our software system configurations, but since that largely stayed the same across prototypes, I will talk about that more later on. Our second prototype of the module had all the same components in practice, but it was all contained on a dev board fitted with the Texas Instruments TDA4VM processor. The processor itself was an absolute powerhouse. Like the Pi, it had a 64-bit ARM processor clocked at 2.0 GHz, 500 MHz faster than the Pi. It also had a 1.5 megabyte cache, much larger than the Pi's. Along with the powerful processor was the rest of the system we had designed before. The device was designed with video streaming in mind, giving us a much more capable platform to start testing for our final design. The important thing to note here is the processor itself, the architecture, and the support for Linux. As I mentioned earlier, the dev board was fitted with the TDA4VM, which was the processor we decided to go with for our final PCB system on chip design. Since this processor was the same architecture as the Pi and would also be running Linux, software compatibility was no longer a concern, as CPU architecture and the kernel are the most important factors when porting software between platforms. This prototype is still a work in progress and has been a large portion of the focus this semester for the systems engineers, while the hardware engineers have worked on the PCB. The power supply was the biggest challenge for our hardware engineers, as various different voltages are required for the system-on-chip implementation that would use the TDA4VM processor. These voltages range anywhere from 800 millivolts to 3.3 volts, and these supplies are separated based on these requirements and tolerances for voltage fluctuations. The power supply also includes a shutdown threshold monitor where the SoC will shut down if voltages fall out of tolerance in order to protect the hardware. Our hardware engineers spent a lot of time reading through hundreds of pages of documentation for the various systems used. The Texas Instruments Octal Serial Peripheral Interface, or OSPI, had quite the learning curve for our hardware engineers to overcome, and required extensive study of concepts that they would not reach until classes they were scheduled to take later in their college careers. When it comes to software, Linux-based operating systems support a vast ecosystem of software, and for that reason we tried two different operating systems on our first prototype. We started with a minimal ARM port of Debian before inevitably switching to Raspbian OS, the standard operating system for Raspberry Pis. For video streaming, we used the GStreamer server and client software, which is widely used across video streaming platforms and devices all over the world. For secure video streaming, we implemented Secure and Reliable Transport, or SRT, which allowed easy integration of AES encryption, one of the most popular encryption standards in the modern age. With our software configuration, we were able to successfully implement secure transfer and encryption and get our video to stream over Wi-Fi. Our transition to the second prototype, which as I mentioned is still a work in progress, was very smooth given the portable nature of our design. The CIRC team encountered and overcame a variety of obstacles during our time working on this project. The biggest issue we encountered was a lack of cell towers for our module to communicate with given our location in the Upper Peninsula. We also had great difficulties getting SIM cards activated for our device, as very few cell providers support third-party non-cell phone modules like our base hat and radio. The vast and advanced documentation for the hardware meant that our hardware engineers had to spend a lot of their time with their noses in the books, especially given that the points they were at in their college careers. Senior members were able to provide some help when possible, and in the end our hardware engineers did very well given the time constraint and their backgrounds. On the systems engineering side, a reconfiguration of GStreamer set us back quite a bit before we transferred over to the dev board for the second prototype, but this was recently overcome and progress has resumed. The steps we recommend future teams take to continue the project would be to complete and test the custom hardware implementation of the module. It would be wise to do so over both local area networks and cellular networks. For this, it may be necessary to test the project in an area where there are more cell towers. In conclusion, we found that this project holds a lot of potential for future application. Given the focus of system configuration and development for this project, reproduction of the hardware would be relatively easy and fast, and could easily be expanded on or even reduced for smaller applications. This project is in its final semester, and we currently are in the middle of our second prototyping stage and the PCB design, though we have found that skills and abilities of our young team have improved greatly during our time working on this project. To close out, we would like to extend our thanks and appreciation to CIRC, as this project and its open-ended nature has allowed us to branch out to a wide range of technologies and potential solutions to a variety of problems encountered throughout. We would also like to thank Staff Sergeant Tippett and Professor Cischke for their guidance throughout this project. I would personally like to thank the rest of my team for their hard work this last semester, and both Michigan Tech and the Enterprise program for continuing to provide these real-world engineering opportunities for students like myself. Finally, I would like to once again thank you, the judges, for the time you took out of your day to review the work we have put in. Thank you, and have a great day.